Welcome back. Now we move to lecture 5, and this is the first lecture on a series of lectures where we'll be talking about the kinetic theory of gas. So kinetic theory of gas is essentially understanding the distribution of velocity and understanding how those properties relate to thermodynamics and thermodynamic properties. And the big thing we are going to do in this lecture, in fact the only thing we are going to do in this lecture, is to derive the mathematical expression for the Maxwell-Boltzmann distribution. And spoiler alert, the figure there that's on this slide is the result that we are going to obtain. This is a very important notion, and again I'd like to show you how we build in this course. The distribution, of course, by now you should be familiar with the fact that when I talk about distribution, I'm really talking about probability. So that's going to give us the probability of finding the gas molecule at a certain speed in this case, right? And so on the y-axis you will have the probability, or in other words the number of molecules really, and on the x-axis you have the velocity. So this distribution here, which is a distribution that's going to depend on the temperature, is going to tell us essentially at what speed we should, with what probability we can find gas molecule with a given speed, and we will find that those properties are going to be relatable to thermodynamical properties. We are going to do that, but we are going to prove this first, how we can calculate this Maxwell-Boltzmann distribution. So let's first set the stage. Again, we are going to work with pretty much ideal gas. I would suppose that they are monoatomic. The reason why we do this is because we don't want to have the complication due to the rotation of the gas on itself, or its vibrational. For example, if you have a diatomic gas, there is a vibration, so there is some energy that can be stored there. We're not going to do that. We're just going to suppose that the only energy that can be in a gas molecule will be due to its kinetic energy. That's basically the idea. So we are making things a little bit simpler, and we will add degrees of freedom later as we move along in this course. There is no interaction, so as I said, there is no interaction between molecules, just the same as we saw for the ideal gas. That means that the only energy, as I just mentioned, is the kinetic energy. They can exchange energy, though. The molecules can exchange energy through collisions. So as you know, when you have a collision, you exchange energy and momentum, and conservation of both during the collision, as you know from elementary physics. We will only consider linear motion, of course. In this case, again, we will use the Cartesian coordinates where in the velocity space Vx, Vy, and Vz are orthogonal, and we do find that the velocity vector will have component Vx, Vy, and Vz, and of course in that case the energy, the kinetic energy, is simply the sum of mvx squared plus half mvx squared, half mvy squared, and half mvz squared, for a total of 1/2 mv squared, where v is the length of the vector in Cartesian space. Something fairly elementary. So what just to set the goal of this lecture is to try to understand the distribution of speed for such a gas at temperature T. So we are going to look at that, okay? So let's have a look at the velocity distribution. And this is essentially the most important slide of all, because it's going to translate what we've learned so far into this particular problem. So imagine that you have a gas of molecule, and we are going to work in a canonical ensemble with constant temperature. And so we are going to imagine a single molecule inside of the gas. So basically there are many molecules in the gas, but we are going to look at the perspective of a single molecule. And for that single molecule, it looks like the molecule is in equilibrium, in thermal equilibrium, with the rest of the gas, which we're supposed to have many molecules. So that looks like the definition of a reservoir is pretty good, is certainly obeyed. So that means that if we can do that, we can use the Boltzmann distribution. The Boltzmann distribution is going to give me the probability of finding the molecule in a certain energy state. But energy states here are defined by the kinetic energy. Remember, the Boltzmann factor is simply a factor that corresponds to the energy of a particle divided by kT. So basically, that's what we will be doing here. We'll consider each molecule embedded in a system connected to a bath, and the bath will be all the other molecules. So remember, the bath, the heat bath, and reservoir are the same thing, as synonymous. So of course, the Boltzmann distribution applies. And remember, this is a distribution, this is a probability, but because we have a continuous function, a continuous variable, which is the velocity, we have to look at the probability density. So in other words, we get the probability not of finding Vx, but the probability of finding Vx and Vx plus dx, okay? And that probability is going to be proportional to a Boltzmann factor that I've just wrote there, where the energy is the kinetic energy. So you have mvx squared divided by 2, okay? That's the most important thing, because of course we know what this looks like. This looks like a Gaussian, right? If you plot the distribution as a function of Vx, this is a Gaussian, which is good news because we know a lot of formula for Gaussian integration, and that means that we will know a lot of things analytically. In particular, we can normalize this function, which simply means that the total sum of all the integral the integral over all the possibilities will give 1. So in other words, we know that all the particles will have velocity, basically, right? Or including 0. Okay, very good. So we are looking at this at only one dimension. The button there on formula would lead me to the formula on the integral using Gaussian. I'm not going to go there because we've done it before, but this is for those who are following with the book, this is in the appendix, or you can find any table that have the integral for Gaussian. We're not going to spend time on this. It's fairly elementary. The point is that that integral is going to give me a number. So the integral of what I found in the previous slide will give me a number, which, since it's not 1, that means that my distribution is not normalized. So all I have to do is to divide by this integral, and I end up with this equation, which is a very important equation. Of course, it's going to give me the probability density of finding a particle. So gvx times dvx will give me the probability of finding a particle, so a gas, a molecule of gas, monoatomic molecule of gas between Vx and Vx plus dx. So this comes directly from the Boltzmann distribution. Again, each time we have a distribution, probability distribution, we can calculate a number of statistical properties, the typical ones. That's a good exercise, again, to apply the rules, the mathematical equation for Gaussian integrals. Can calculate the expectation value. Of course, we have a Gaussian, so we know the expectation value is going to be 0, right, as always, because of the symmetry around Vx equals 0. What's more interesting is to calculate the expectation value of the absolute value of Vx, and of course also the expectation value of Vx squared. We know that the expectation value of Vx squared is going to be important for our purpose, because we know that the kinetic energy is mvx squared over 2. That means that it looks like it's important if we want to know the expectation value of the energy. It looks like it's a good idea. And of course, again, another spoiler is that we find already that the expectation value of Vx squared is kBt over m. So that's already telling us about what would be the expectation value for the kinetic energy along the x-axis. Of course, it will be kBt over 2, since the kinetic energy is mvx squared over 2. Anyways, I'm jumping the guns a little bit here, so we'll get back to that in a few minutes. Okay, so this is just in one dimension. So this is the probability, gx times dvx is the probability of finding the gas molecule between velocity vx and vx plus dx. Okay, that's not quite what I want to do, because we live in a 3-dimensional world, at least in Cartesian coordinates. So what I'm interested in is a total probability, and here it's a mouthful, but I'm going to say it anyways. That's the probability that a particle has a velocity along x that's between x and x plus dvx, between vx and vx plus dvx, times the probability of finding that particle with the velocity along y between vy and vy plus dvy times the probability of finding that particle velocity along z in vz and vz plus dvz. That's it. So it's a product, of course, because probability of compounded processes is always given by the product. The good news is that in my treatment that I did in the previous slide, I just picked an axis randomly, but it could have been any other axis. So the math is described the same way. In other words, we can replace the GVX and GVY and GVZ by what was found in the previous slide. What's nice about this, of course, is that because of the exponential, the product of the exponential is the exponential of the sum, and I end up with this formula, which is nice. So the probability of finding the particle in that box in velocity space, right? Remember, it's a box that's between Vx and Vx plus dVx, Vys and Vy plus dVy, Vz and Vz plus dVz. So the probability of finding it in that box is given by this formula. With v square is vx square plus vy square plus vz square. So that's all very nice. The problem is that probability is essentially useless because this is a probability of finding the particle in a small box. But what I'm really interested in is the probability of finding the particle with a given velocity, or actually given speed, right? The scalar version. So what's the probability of finding the particle with a certain speed, like say 5, 7, okay, something like that. So that's not quite what I have here, because this one is just the probability of finding a particle in certain cube in the velocity space. So instead, what I need to do is in that velocity space is I have to look at all the places where the velocity vector end up in a shell of radius v and thickness dv, right? That would give me, if I can find all the particles in that shell, external shell, then I would of course get the probability of finding the particle between with speed v speed between v and v plus dv. And of course this calculation is not very complicated to do when we remember that the volume of that shell is going to be the surface of the shell times its thickness, and of course the surface of a shell, it's basically the surface of the sphere, which is 4 pi v square, and the thickness of the shell is dv. So the volume of the shell is 4 pi v square dv, and I know the probability that I find to find a particle in any of the box that I just described in the previous slide on the shell is the same. It only depends on the speed, right? It only depends on v square. So that allows me to write, of course, the equation that's on the bottom left of this slide. There is no 4 pi because we have this is proportional, right? We have the proportional sign, so we can leave the 4 pi within the proportional sign. We will need we are going to need to normalize anyway, so let's not worry about that. What matters though is that now the probability of finding the gas molecule between v and v plus dv is v square times the e minus mv square over 2 kBt. So that's the v square in front there just comes from the fact that we are integrating over a sphere. All right. So that's very usual that what we have, that each time we work we are interested in distribution of length or speed versus a distribution of the component. We often end up with a quadratic term that's simply coming from the surface of the shell that we are integrating over. So that's nice. We have this, and we're almost there. This is almost the Maxwell-Boltzmann distribution. To get the Maxwell-Boltzmann distribution, again, we want a distribution. Therefore, we need to normalize, and to normalize, we integrate this one more time. This integral is actually fairly straightforward when you have the formula from mathematical tables, and you end up with the prefactor. And the prefactor is important because the prefactor is going to be to make sure that this is a true distribution where the total probability is equal to 1. Okay. So what's nice about this now, and this is what's in the red box because it's a very important result. It's called the Maxwell-Boltzmann equation, which again, what it gives you is the probability of finding the gas molecule at a certain speed, right? Speed is the scalar version. So basically the length of the vector, all right? So that's very important because you see that the maximum is no longer at 0, but it's actually at as an exponential would be, right? The decaying exponential, the maximum is at 0. Instead, the maximum is at a finite value, and the reason why you have this is because you have the v square in front of the equation. Okay, so that's all very good, and we also know that this equation is going to depend on the temperature. I like to attract your attention. There is a temperature in the exponential, but also in the prefactor. One more time, we have a statistical distribution here, so we can calculate different things like the expectation value of the velocity. The expectation value of the velocity is going to be given by another Gaussian integral. The expectation value of v square, which is actually very important because the expectation value of v square, as I just mentioned a few minutes ago, is going to be related to the expectation value of the kinetic energy. And what we find is that we have essentially a kBt over m term contribution for each dimension. So if you had a particle that be confined into one dimension, the expectation value of v square would actually be just kBt over m. If it were confined in 2 dimensions, it would be 2 kBt over m. And of course, in 3 dimensions, like we've done here, it's 3 kBt over m. And the reason for this is because the expectation value of v square is actually the sum of the expectation value of vx square, vy square, vz square, as we have seen in the first lecture about the expectation value of sums. Okay, so we can also calculate the root mean square of velocity, which is of course the square root of the expectation value of v square, and that gives me also a statistically important result. So one thing that I already alluded to a few times in this podcast that I'm going to repeat is with the final equation is the kinetic energy. So the mean kinetic energy of a gas molecule in this description we have is going to be equal to 3½ kBt for the reason I just gave you before. And again, the 3 comes from the dimension. So we've essentially proven a very important result already right here. Okay. So just to repeat something that I already said, but in one single slide now, this is essentially a very good summary of what we need to know. This is the top is the Maxwell-Boltzmann equation. It's the distribution. We have the value of the maximum. So to find it, you just derive f of v and find the maximum value, the expectation value, and then the root mean square. And if you see that they only differ between each other between a factor of square root 2, square root 8 over pi, and square root 3. So that means that you see directly that Vmax is smaller than the expectation value of V, which is itself smaller than the square root of the expectation value of V square. So those 3 values there can be plotted on the distribution, and you see that you have this asymmetric distribution. This is the Maxwell-Boltzmann distribution. It's a very good idea to have a picture of this distribution in your head, and also know what it looks like. I mean, even if you forget what's the prefactor, it's fine. You can find it or can provide it to you. But the point is that it's very important to have a picture of what it is. If you look into the textbook that we are using, there is quite a bit of discussion about how historically people have been able to measure this distribution and to see that indeed it follows exactly this, and it was done successfully. I'm going to skip this part in this screencast, but instead I'm going to show you an example on how to calculate the root mean square speed of a nitrogen molecule at room temperature. You see that it's actually the only difference that we have, the only thing that we have to worry about in terms of nitrogen molecule is the mass, right? So Kb is a constant, T is a parameter of the problem. So the mass, we know the mass, we know the mass of a molecule, right? And the mass is just simply given by the molar mass divided by the Avogadro number. And then we find that we find that the velocity, the root mean square velocity of this nitrogen molecule in a gas is about 500 meter per second. Okay, I should say something here. Nitrogen N2 molecule is not monoatomic or anything like this, but this is so I understand that the constraint that we gave ourselves to start with are not exactly met with this molecule, but that's fine. It doesn't make much difference. The point is the order of magnitude of this velocity is 500 meter per second. So I'd like you to realize that 500 meter per second is extremely fast. It's actually it's the same order of magnitude as the speed of sound. So you see this picture we have sometimes of this molecule that are moving around and maybe moving kind of randomly and so on. They do that, yes, but usually the picture we have in mind, the intuition that we have developed over the years from what we learn, is something that goes pretty slow. We have to realize that when you have a molecule at room temperature, it goes about 500 meters per second. So you have to realize the number of collisions that you have, for example, with a vessel or collision between other molecules. They are really, the velocity, the pace that's relevant to this problem is about 500 meters per second, so which is about the speed of sound. So this concludes this screencast with a summary. The summary is pretty straightforward. We have studied the Maxwell-Boltzmann distribution, which provides the probability density of finding a molecule of gas between a certain speed, within a certain speed range. And we've studied also the expectation value of V square and expectation value of V. And again, don't be confused here. The expectation value of V is not 0 because we no longer have a symmetric distribution. Okay. And we don't have a symmetric distribution because we are integrating over all the possible states that correspond to a given speed. Okay, because of course other different combination of Vx, Vy, and Vz will give us a different value. Will give you the same value of the velocity. This is where the velocity vector actually just scan a given shell in a velocity space in Cartesian coordinates. So that concludes our lecture 5. The next lecture will be about applying all this to the pressure of the gas. Thank you.